Hi, everyone. Welcome to today's webinar. We are going to be talking about efficient access and haul road design, and really taking a moment to focus on some of those efficiency and optimization tools that are part of the workflow that you can leverage to make that design process a whole bunch easier. My name is Erin. I'm going to be your webinar host for today. And with me, of course, our resident webinar presenter, we've got Matthew Dickey. He's our training manager here at Softree. In terms of webinar format, if you haven't joined us for one before, you are going to be muted for the entirety of the webinar. We're going to do a little bit of screen sharing, and we tend to keep our cameras off just for bandwidth for folks who are joining us from overseas. And today's webinar, worth noting as well, we do have a few products and variants. Today's webinar is going to be done in our RoadEng Civil Engineer with Softree Optimal software. So in terms of what we're going to talk about, today's webinar really is all focused around access and haul road design. And when we talk about access roads, this is really something that there's a whole bunch of different types of access roads spanning a whole bunch of different industries, whether that is in mining, forestry, renewable energy like wind farms, transmission line roading, and other resource development. And although there are nuances and differences between, say, the cross-section or some of the design standards like curvature and grades and design speed between these industries, they all share common design goals. First and foremost, are the roads safe for use? Are they cost-effective? Are they environmentally responsible? So today, we're going to explore how RoadEng really can help to streamline that process from terrain modeling, landscape level alignment selection, detailed design, and earthwork optimization. So that's kind of our plan for today. So in terms of our design goals, as I mentioned, they all share a lot of similarities, whether that's the safety and reliability of the road, making sure it's got the proper grades, curvature, drainage structures, erosion control, really making sure that it is safe for use for the intended audience, essentially. The next one is, in terms of design goals, is cost efficiency. Can you make the road more cost efficient when it comes to the construction of it? More cost efficient when it comes to the future maintenance of it? And I'll be honest, more cost efficient when it comes to the design process behind it. And then our other goal that we'll be sort of looking at as we go through this process today really is the environmental sustainability side. You know, are we able to minimize the land disturbance? Can we protect environmentally sensitive areas? Are we minimizing stream crossings? And really, can we reduce that impact that the road has on the environment through maintaining natural drainage patterns, et cetera? So to achieve these goals, we're kind of breaking the process down into 4 key steps. And from a format perspective, we're going to kind of do a step or introduce a step, and then we'll head into the software to see what that looks like. So the 4 steps, we've got terrain modeling. And really, this is about defining our original ground and some of these conditions. Streams and drainage patterns are certainly one of those that we're going to want to define in the terrain modeling side. Identification of preliminary locations for the road, really answering that question of where do we put the road, and more so, where's the best place to put the road that helps us to achieve these design goals. Then we'll take a look at spelling error on the PowerPoint slide, which I'm totally embarrassed about. Geometric design, what does our road look like in detailed design? And then we'll take a look at sort of that more detailed optimization, which is what we call profile optimization, which really is how do we minimize the cost even further. So for our first sort of step, we're going to go look at terrain modeling and data preparation. Here, it's all about importing the survey data, creating a 3D terrain model, identification of watercourses, streams, and ponds, and then identification of potential additional zones or areas of higher cost. And these could be, you know, geotechnically unsuitable areas. They could be environmentally sensitive areas. We can bring in these additional zones either through importing, say, polygons from a GIS platform or the creation of features ourselves. So with that, I'm going to do our first flip of the presenter. It's going to head over to Matt, and we're going to take a look at terrain modeling.
And as per kind of our typical process, we're going to start right from square one, and we're going to bring that data into terrain. So I've opened up the terrain module. I'm going to click Insert. I'm going to start here by bringing in my surface information. So in this case, my surface information is DEM, so LiDAR-derived DEM data. It's in a TIFF. We're going to hit OK. Of course, the TIFF could be an image or it could be a raster, so we're going to select that it's a raster. And we'll hit OK. And, well, we can see that big magenta blob being drawn. So that's all of the, I guess, pixels in the raster that are going to be used to make up our surface. Now, with this is a fairly large area, a fairly heavy file, and I can see I've got about 40 million points in my file. So here, I'm going to just thin my data, and since it's DEM data, I'm going to use the feature simplification tool. So that's in the feature tools ribbon. And we're going to just put a tolerance on here, and we'll hit OK. And we're going to keep the important detail of our surface where there's kind of changes in slope, but we're going to remove some of the redundant information within that tolerance that we had set. So we've taken that 40 million point file down to a 3.4 million point file. We'll click Generate. And we're going to turn this into a surface. And we'll create contours here while we're at it.
And while that surface is generating, it is useful to note, Matt thinned his data, but this thinning method is very specific to raster DEM. So if you're working with LiDAR, you're going to want to leverage the simplified tool that Matt is hovering on right now. Yeah.
Cool. All right, so I've got a surface, and we can kind of zoom around. We can see the kind of the details of what we're looking at. For this particular project, I'm going to bring in a few extra items to add context, and some of them are going to be important considerations for this project in particular. So to bring in extra information, I'm going to click Insert File. Now, this project, as introduced, we're going to do it in a generic sense, but we have a polygon, and that polygon represents the property limits, so the least limits of where we'd like to keep our road within. So that's one thing that we're going to want to consider when we use Path Explorer later. Now, the other thing that we're going to want to do, and here we don't necessarily need to do it, but if we want to know, well, where's that destination that we want to get to, we can bring that in as well. I'm just going to make it a little easier for everyone to see. So that's our goal. And of course, if we want to get a road to that point, well, we probably are going to want to consider a lot of things. A lot of those things are just kind of accounted for when we have a surface, but streams are going to be pretty important as well. So I'm going to use our hydrology tools. I'm going to run the streams and ponds tool, and then we'll be able to see where we expect streams to channelize and where we expect there to be ponding water. And there we are. We can see kind of where those streams are likely going to be at. And with that, I'll hand it back to Erin and let her introduce the next topic.
Okay, excellent. So our next topic, now that we've got our terrain model built and some of that additional information added in, is really all about figuring out at a landscape level where do we put the road? And really, where do we put the road that minimizes cost and that really meets our constraints and other considerations? So in this step, we're going to identify the start and end points, or the start point and the end destination for where we would like our road to go. Then we're going to go in and define our constraints. So again, higher cost zones, minimizing stream crossings, grade, curvature, road width. We're going to put all of those types of constraints into a tool in the software called Path Explorer. From there, Path Explorer is going to go and literally iterate through hundreds of millions of options in order to narrow in and find the most optimized paths it can, given all the information it has. And then we'll review those options and take one of them out to the next step after that. So with that very brief introduction, I'm going to go back to Matt.
Yeah, so when everyone saw the screen last, we had set kind of everything up that we want to consider, but we haven't told the software exactly what we wanted to do. So I have that point just indicating where we want to get to. It doesn't have to be a point that we bring in. It could just be a feature that we draw. So I'm going to create a new feature, and well, I want this road that we're going to do. So it's going to start there, and I want it to go up to here. Now, of course, again, we don't necessarily have to use that point. We could go anywhere that we like, but that's the spot where we want to go here. So we've got that feature selected. While that feature is selected, we're going to go over to our optimization tab. We're going to click Path Explorer AI, and we're going to put in our design parameters. So with this, I'm going to tell the software I want to have a 100-meter radius curve, a minimum curvature of 100 meters. I want it to give me 5 options. I can set my road width to be whatever I'd like. I can set my cut and fill slopes to be whatever I'd like. I'm going to keep this road fairly not aggressive. So I'm going to try to keep it at max grades of 10%. The software is really looking at cut and fill costs to figure out where that cheapest spot to put the road is. So it's only considering places that you can go given your design criteria, but it's looking for the cheapest way to get there given the earthworks. So we've got our dollars per cubic meter for cut and fill, and then dollars per square meter for our surfacing area of the road. So if we hit run, the software would do its thing, and in this case, probably give a reasonable solution. Even without accounting for anything else. My guess is it probably would come over here and cruise around and get there that way. But in this case, that property line, I don't want to go outside of that. And I also want to take into account that my streams are going to cost more than just putting the road on nice dry ground. So for that, I'm going to go into the construction zone editor. And I'm going to say, well, we're going to make a new construction zone. We're going to use polylines. So the streams themselves are going to be used as a crossing cost. So I'm going to say each one of those streams is $5,000. And then to keep it within this property limit, I'm going to go in here and I'm going to say, well, we've got a no-go polyline. So I don't want to cross that line, and that's not a try not to cross that line. That's a hard do not cross that line. And I forget what that, there we go. We've got that feature called mine site. We're adding that in as a no-go polyline. So we've added extra spatial considerations here, but of course, if we had other polygons that we didn't want to go into a polygon, we could make a no-go polygon. Or if we had areas where we expected things to be more expensive, maybe shallow bedrock, we could add a polygon with increased earthworks costs. And then somewhere in between the two, if you had something that was, well, not a absolute don't go there, but if I can avoid it, I'd really like to avoid it. Well, then you could add in a polygon with just an artificial cost added in there, and that artificial cost could be more of a penalty than a real cost. So we've got that. And then the last thing that I'm going to do here is I'm going to say, well, at the start of my feature, I want to keep this thing pointed in, well, I want it to start out pointed in that direction. And we'll hit OK, and we'll let this thing think. So that's going to think. I suspect it's probably going to take a minute or so to do its thing. But yeah, it's going to go through the process. It'll probably take 40 seconds or so to well, find a solution. And we'll see as, oh, it didn't take as long as I thought. And so it's found 5 paths, but it hasn't narrowed in on having the best group of paths selected. So we'll let it go here for a bit longer, and eventually this status is going to change to found 5 paths, unlikely to improve further. And at that point, we're going to hit cancel.
Yeah, and I think it's also worthwhile just to mention, so the output of this process here, and it's already done it, is going to be a whole bunch of polylines. But behind the scenes, Path Explorer was really looking at full 3D cross sections through a 3D space. So although these solutions at the surface look very simple, it is looking at them as a true 3D problem. And we'll show you how we convert that into a proper looking 3D graphic in a couple steps. But yeah, sorry, Matt, that was very fast in solving.
That wasn't bad at all, was it? All right. Yeah, so we've got 5 solutions. Now, for these, we can kind of visually assess and see, well, maybe this one's worth pursuing and that one's not. Yeah, we can click on them to kind of highlight what we're looking at. But if we want to see which one of the select options is cheaper, well, we could go in here and we can see that. So XPath 521K, that 521K is the expected cost given the metrics we've provided it. I'm going to just get rid of all the others just to avoid some clutter. So we've got that solution is our cheapest to have a well, curves with a 100-meter minimum. Now, considering how quickly we just figured out that alignment, one of the other really nice things that we can do here is use the tool for kind of optioneering and weighing our different options. So rather than just considering the 100-meter curve option, I'm going to say, well, what happens if we keep this, well, we allow the road to get wiggled around a bit more. So I'm going to go with a 35-meter radius curve. And
Matt, don't forget to press the uncheck the remove existing features button.
Yeah. That's, oh, I guess I'll do that again. All right. Yeah, so here we go. And yeah, so it'll be a similar time, but now we'll have 5 different options that are considering an entirely different design criteria. And I mean, here I kept my grades at that same constraint. My streams all cost the same, but you can really change whatever parameters that you'd like. So if I wanted to weigh the option of having my road scream up the hill at 18% versus 10%, well, I could just click that, wait a couple minutes, and away we go. So it's nice from well, if you're a project owner, to make sure that you're considering, well, I can go faster on this road, but it's going to cost more. So faster is good for reduced cycle times, but costing more to construct is bad. So you can weigh those options from an informed perspective. Yeah, and if you're a consultant dealing with a client, well, you can and there we are. So we've got some pretty similar solutions, and we'll come in here and, well, instead of being 521, we're down to 450 for the cheapest option with that. So yeah, it's nice to have options, and nice to know the cost of what making those different decisions are going to impact your project. So with that, I will save this. So this is my terrain file. I'm going to just save it as topo, and I'll hand it back to Erin.
As we've gone through the last two steps, creation of a terrain model, identification of some features like streams and ponds, landscape level path exploration, and really from there, we move into the second module of RoadEng to do the geometric road design. So in the second module here, we're going to take our selected path exploration features, could be one, could be multiple, and really turn them into proper geometric alignments, horizontal and vertical, and attach to them a detailed cross section, and make sure we've got our road class specifications set up, and really, kind of take it from what right now is seemingly a line on a map into full 3D road design. So, very brief introduction. Gonna go back to Matt, and he's gonna take us into the next module and show you how to turn that polyline into a proper alignment with curves.
I saved my terrain. I'm going to minimize this, and we're going to jump into location. We're going to click new file. We're going to reference that topo file that we've just created. Here I've got my feature that I want to run with. So I'm going to go with the cheaper option. We're going to evaluate that in more detail here. We'll click next, we'll click done. And well, we can see a few things. So right off the bat, this particular project, I probably don't want a paved road in this situation. So it's defaulting to my default rural road cross section. And I'm going to set up a template that captures the geometry that I'd like. So in this case, I'm going to keep it as kind of a typical access road, resource access road, so a gravel road. But if this was a haul road, we could very easily set up a cross section for that as well. So I'll set both of those up and talk about that before we go on to our next step. So for the access road side of things, most industries would have something that looks at least similar to this, if not identical to it. So this default cross section is called a resource road. The template itself doesn't have a lot of information that we can customize in it, but if we expand this, we have the template components in there. So if we double click on this template component, and if we want to run with an 8-meter wide road, well, we can change the width to 4 on the left. We can set our surfacing depth to whatever we like. And as we make these changes, it updates in real time. If we want to have it symmetrical, we can just, well, we could make the change on the other side, or we can just delete the other side and copy and paste one. Now this template editor that I'm in, it's kind of like a sandbox. We can pull it around and see how things are going to interact before we use it. So I can see my ditches, I can see the ditch depth, slopes. I've got my slope set to auto. I am happy using this for this project. But if I was doing, well, if I was doing a forestry haul road, well, it's probably the same prism. If I was doing a mining haul road, well, I'm probably going to have berms. If I've got big cuts, I'll probably have bench cuts in there. And for that, we can put together something fairly quick. So I'm going to use this as my starting point, copy, paste as new. Now I'm going to get rid of the roadway components. I'm going to go on to the E-library, and I'm going to bring in these component folders. So here for my mine haul road. I'm going to use this template down here. We can configure it as we wish. So I'll go a little wider for this one. I'll add a berm on it. So this, if we pull it up and we have a drop that's high enough, it's going to automatically add that berm for me. And here, if we pull this down, well, we can see our cut slopes are just the well, stepping up the slope. And it won't be very interesting in this case since it's so small. Well, not so small, but we won't have any crazy deep cuts, I don't think. But we could go in here and we could say, well, I want my cut slopes to be benched. And if I want my benches to follow the grade of my road, I can use this one. If I'd rather those benches stay level or at a specified grade that's independent of the road grade, I could use this one here. So we can come in here, we can set that, we can put our parameters to match whatever we'd like. Now I don't want this to be applied in fill, so we'll turn that off and copy, paste. And usually here you're going to want it to give it a name so it's easy to keep track. And here again, we can test it. We can see how that's behaving in the cross section before we apply it. But yeah, we've got both of our bases covered. And once you've set up any of these things, you can save it and have it included as your default, so you don't have to mess around with it every time you start a project. But just to reiterate, for this one, I'm going to just keep it simple. Use my resource low volume road, and I'll hit OK. I'll hit OK, and I'm going to apply that resource low volume template. So we apply it by station range, and from dot to dot is the whole thing. And we could split it up with different templates along different sections of a road, but I think this is going to be appropriate for the whole thing. So that's kind of one important design consideration. The other thing is the output that we get out of Path Explorer is a polyline. So if we zoom in here, we can see each turning point has an IP, and we could totally move things around and add curves manually. But we could also come over here and we could say, well, let's give this thing some specs. So I've told it 35-meter radius curve. I'll give it some wiggle room to not follow the line exactly, just to simplify any minor undulations. And we'll let this thing go, and it's going to convert that to a polyline. And it's going to take a minute to think as it narrows down on, well, where to put those IPs to, one, minimize our offset, but within that tolerance, use as few curves as possible. And we are set. We have an alignment screaming up the hill that's, well, a horizontal alignment anyway. And if we were doing kind of that traditional workflow, we could go through and we could manually, well, design our, tweak our horizontal if we wanted to make adjustments. We could design that profile if we want, or we can use vertical optimization, and I'll let Erin introduce that one.
Awesome. So this kind of brings us to our final step in the process, which is the more detailed alignment optimization. So again, we've done the terrain model, an initial landscape level optimization using Path Explorer. We've gone and kind of created the foundations for our geometric road design. And now we're going to leverage vertical profile optimization in order to minimize the costs further. And really what vertical profile optimization is, it's a complex mathematical optimization where we look at all the cuts and fills in the road design, as well as the material movement costs for how that road's going to be constructed. And what the software does is it looks to minimize those costs, minimizing all the little cuts and fills in order to generate a more balanced lower cost for the subgrade construction alignment. So here, in terms of what we do stepwise, you can define your materials that are in your project, as well as the unit costs. And I want to just put a gigantic asterisk here. Maybe it should have been larger on the slide. This part really only needs to be directional, because at the end of the day, a road that cuts and fills and moves less earthwork is the cheapest road. And I know sometimes people get very hung up that they do not have precise material costs that they're integrating into the software. And really, it's not necessary, as long as your relationship between the materials, if you've got, for example, you've told the software that there is rock along your alignment at a certain depth, and you have gravel or some other materials, as long as the relationship between the costs is directionally accurate, the output of vertical profile optimization is going to give you the road that costs less to build and less to construct. So step one, define the materials. You can look at your unit costs. Step two, adding control points, K values, other material movement constraints. I wrote a plus because there's a whole bunch of different things you can do within profile optimization to constrain your alignment. And then we'll move in to the third point here, which is actually going and essentially pressing the button to get the software to create that profile for you. And then the fourth option, very much optional, which is optioneering. So kind of like what Matt showed us with Path Explorer, adjusting the variables, adjusting some of those settings and standards. We can do that here in profile optimization as well to help you really iterate and explore what different elements have the impact they have on cost. So for example, if you change your design speed, it'll allow you to quickly compare that. So enough from me. Matt, back to you.
Yeah, so previous step, basically we started our location file, and rather than actually designing our whole alignment manually, we just set things up. So we've got our cross section the way we'd like. We've got our horizontal alignment as a proper alignment. And now we're ready to, well, configure this so the software figures out our vertical alignment for us. Big driver here is, again, earthworks costs. So I've just got my default ground type assigned. Now we can have different ground types and different horizons assigned at different locations along our road. But I'm telling it, excavation costs $12 a cubic meter, embankment costs $4 a cubic meter. But this is also going to include that mass haul cost, so your longitudinal movement along the road. All of these are customizable. You can make them whatever values you'd like, but as Aaron said, ultimately the software is going to try to minimize your cuts and fills, and yeah, as long as your, well, an example would be as long as your solid rock that's going to require drilling and blasting costs more than your gravel, it should give you a reasonably good solution without worrying too much about the details. So earthworks cost is going to be the driver. We're going to go over to the Project Explorer panel, right click, vertical options. We're going to tell the software, well, our design criteria here, I want my grades, so 10% plus and minus. That happens to work with what I said in Path Explorer, so I won't change that. Here, though, I'm going to run with a fairly well, slow road to match the tighter horizontal curves. So sags of 4, crests of 3. We'll hit Add Edit. We'll click Add to add a control point. So I want to tie in with the existing infrastructure at the start of my road. And well, we could add in a bunch more nuances. If we were building a road across a steep face of a mountain, we could add full bench constraints. If we were building across muskeg, we could add a minimum embankment height. Yeah, add pits, material movement considerations, but most of the time keeping it pretty simple is appropriate. So I'm going to just hit process. I'm going to set that as that. And we're going to let this think again. So this is going to run through, and it's going to kind of like Path Explorer. It's going to take a minute to figure out the best solution. And we'll have a alignment. So if we can look at our mass haul here. We can see right off the bat, we are balanced. So that's a good sign. We can also see that for most of our road, we've got some pretty small material movements. So that's a good sign as well. And then at this particular spot, we can see, well, we've got some bigger movements. What's going on there? We can zoom in and we can see, well, we've got a big fill followed by a big cut. So that material is getting flopped back. The solution makes sense. And if we want to see how much this thing is expected to cost based off the earthworks costs that we've put in, you can see we're at $346, and that's thousands, so $346,000. As we review, we can come over here. We can get that breakdown for how much dirt are we actually moving for this one. And we're at 21,000 cubic meters, 3,000 cubes for our surfacing material. And really that's the optimization workflow. Now, as you take it further, of course, you can add in your culvert locations. And here I happen to be right on the saddle, so we probably don't need one there, but I'm sure there's going to be somewhere else that we'll want to add a pipe in, like right there. So we've got our pipe, and we could add those pipes as needed everywhere else. Then we could go to our multi-plot editor, and we could add in our various views. So this would be building out the documentation. We could add in individual views, or we could go onto the web library and bring in a pre-formatted chapter to use as a starting point. But once we've set up our multi-plot once, we can save that multi-plot book layout, and we can use it in the future for our next project. So here I've got my plan over profile all set up and matching the format that I prefer. And then I've got our sections. And of course, we can change how frequently we're seeing those cross sections if we wish as well here. So maybe instead of every 5 meters, we'll go every 20. And with that, we'd hit print. The other thing that we probably would want to do is file, save as, and we can take this out in a format for construction, staking, field review. If we want to pass it back and forth with other software, we can. It's just a matter of selecting whatever file extension you'd like to save that as. And just a note, I mentioned field review. If we save as, where is it? An Avenza file, that gives us a georeferenced version of this that we can take out, use on the Avenza app, and collect more information.
And with that, thanks, Matt. Thanks, everyone, for being here. Thanks, everybody.
Thanks, everyone.